Okay, this is a sample problem for forced convection wherein we will have to do trial and error. So I am drawing here the diagram for this problem. The length of the pipe is given as 1 meter. The diameter is also given, the mass flow rate is also given, and steam condenses outside. Steam condenses outside, which maintains the inner wall temperature at 110 degrees Celsius. Water flowing inside the pipe, let's say at this direction, so it enters at 25 degrees Celsius. The exiting temperature is not given. So this is mainly the reason why we're going to do trial and error here. So the exiting temperature is given. As you know, if you know the mass flow rate of a given fluid, if you know its uh, specific heat and the change in temperature, you can obtain the rate of heat transfer. By the way, this table here is the properties of water. Summary of the properties of water. So we can obtain Q, and then from that Q, we can use another expression for Q, rate of heat transfer, wherein we can obtain the H. Because actually in this problem, we are trying to know what is the value of H other than knowing the exiting temperature of water. So basically, these two expressions for the rate of heat transfer, we need to equate them. We need to equate them later. But how do we start with our computation? Because before we lead here, H is going to be obtained by using the Nusselt number, using an empirical equation for the Nusselt number. And that empirical equation for the Nusselt number that we're going to choose will depend on the values of our Reynolds number and Prandtl's number. Okay, so I will lead you on the steps on how to proceed with this problem. The first step you're going to do is to assume an exiting temperature. Let's say we start with 80 degrees Celsius. Okay, okay, so by the way, I didn't explain this further. The first expression is T out, T in. Change in temperature, you can get to Q. For the second expression here for Q, T wall minus T bulk. If you look at it here, say this is the temperature of the wall versus the temperature of the bulk fluid. So the change in temperature, the difference in temperature allows you to compute for the Q. But the problem is the temperature of the water changes as it progresses from from right to left, from the entering to the exiting. So that's why here wall temperature is constant. We assume it to be constant because of the condensing steam. The condensation happens at a single temperature, and the bulk fluid, we consider the average. We can actually expand this expression into this expression T wall minus, okay, let's say T wall in this part minus the temperature of the bulk fluid here, the second part, plus T wall and then bulk temperature at the entering part divided by 2. This is for the average of the value. If you add T wall plus T wall, that is 2 times T wall divided by 2, you will get this value. T out minus T in divided by 2, you will get this value. So I forgot to explain this equation. Okay, but we will be needing this form of the equation because we need to explicitly solve for T out. Okay, so let's proceed with the calculations anyways. So trial number 1, we start with the assumption that the exiting temperature is 80 degrees Celsius. Remember, okay, notice that it is not given here. 80 degrees Celsius is not given here. It is assigned by me. So as to proceed with the calculation. So with an exiting temperature, we can have an average bulk temperature. Average bulk temperature. How do we compute that? 80 plus 25. Basically, the average of the entering and exiting. $52.5. So why do we need to take the average of the entering and the exiting? Because that allows us to obtain uh, obtain properties of the water at the average temperature. So here we will be viscosity at bulk. We will be obtaining the density of water at the bulk temperature, heat capacity at the bulk temperature, viscosity at the bulk temperature, thermal conductivity at the bulk temperature, and the Prandtl number. Thankfully, we won't be needing to use this equation because the Prandtl number for water is already tabulated here. So we will be performing a, what do you call that, interpolation between these values because 52.5 is in between these two. In order to get the H for later use, we need to use an empirical equation for the Nusselt number. But to decide what form of Nusselt number, which of the empirical equations available out there are we going to use? We need the Reynolds number. And Reynolds number is density, velocity times, okay, I mean the pipe diameter times the velocity times the density divided by the viscosity at bulk temperature. But there's also another equivalent form that we can use based on what's given in this problem. So we can also compute for the Reynolds number given the pipe diameter, mass flow rate of the water inside, cross-sectional area, and of course the viscosity at the bulk temperature. So Reynolds number, and this is pi over 4 because again cross-sectional area. Reynolds number is 56316.46, and we can obtain an appropriate expression for the Nusselt number based on the Prandtl number and the Reynolds number. Now actually I have one prepared here, and this is an empirical equation for the Nusselt number by this author, and based on the range where it is valid, our Prandtl number is 3.5. It is inside this range. Reynolds number inside this range, 46,000 inside this range. So we have a value for R, Prandtl number at bulk. We don't have value for F and K, but the expression for F is given here. This is 46,316.46. You plug it here and you will get the value for F. This one, Prandtl 3.563. And I forgot something, and that is Prandtl's number at the wall. So the wall temperature is 110, and you need to interpolate here because 100 is in between this value and here. So you do the interpolation and let's see what Prandtl number will obtain. 1.6577. Okay, so kindly compute for the value of F and K. Okay, so once again, 3.563. This is 46316. Okay, plug the value of K here, this one, and then plug the value of F here. Let's see the value of Nusselt number. Alright, so the Prandtl number, the Nusselt number is, yep, and then we still don't know the H. Diameter is 2.5 cm, and the value of K now what is H? That is the value of H that we are now going to be using. I'll be using a different color. So MCP D out D in H, we plug it here. Even though this H is the result of speculating an exiting temperature, we're still gonna place it here. We're gonna leave the exiting temperature as the unknown. A A here is pi dl, basically the surface. I mean the surface area. You see here inside the pipe, pi dl, and then we will be using this form d wall d out, d wall d in over 2. Now what is our mass flow rate? 4.185. Okay, remember here the unit is in kilojoule per kilogram Kelvin. I will be using, I'll be multiplying it by 1000 in order to make the units joule per kilogram Kelvin instead of kilojoules, because later on the units here is watts, and watt is broken down into joule per second. I want to be able to cancel the joules here. That's why I need the specific heat capacity to be in terms of joules. Once again, this is unknown. And pi dl plus 11025 over 2. Solve for t sub o. The value that we obtained here is the one that we're going to use for the third iteration. We're gonna do this again. We're going to obtain the average bulk temperature for the second trial, obtain the properties again, and repeat. So the value I obtained here is, okay, 43.38 degrees Celsius. So that is too far from our initial guess of 80 degrees Celsius. So if I do another interpolation, I expect this value to, because this is high, to go lower a bit, probably 41 or 42. Let's see. So we'll do another uh, iteration. Now that means for trial number 2, we're going to start with T out at the same value as what we obtained from the first trial. So now our average bulk temperature is 34.19 degrees Celsius. Okay, so 34 is in between these values. So you do the interpolation at this section. Okay, and we're gonna write it down here. The Prandtl at the wall temperature, we're still gonna be using 1.6577. Alright, now we are set for another round. Okay, first of all, again, Reynolds number to see if it's still valid to use that empirical equation. Okay, Reynolds number 3441188. So, as you can see here, Prandtl's number is 4.9, still in this range. 34, still in this range. So let us just 34411. Yeah. Now we going to compete for the K and the F. Okay, F and K are now available. We can now obtain the Nusselt number. Once again, H, D, K. Okay, now we're set to equating the Q once again. So once again, times 10 raised to 3, so that is joule per kilogram Kelvin. Temperature out is unknown. Okay, nice. So 43.38 after the first iteration, 41.69 at the second iteration. For the third iteration, you can do that on your own, but you see that the difference in temperature, let's say that 43.38. We started with 80, right? You started with 80, and then after the first trial, 43.38, and now at the second trial, 41.69. The next value you will obtain is somewhere around 40 to 41 for the third trial. At the fourth trial, it will probably fall within this value. So probably I'm not gonna try it, but you will see that as you progress to the fifth and the sixth trial, the values you will obtain, or probably you will stop at 41 here, 41 to 42. The values obtained will not change too much, and that value you will obtain at the subsequent trials for T, that is the final answer that you will write for this question. Letter B, the exit temperature is around 41.69. So let's just say 41.7 degrees Celsius. That is your estimate for the exiting temperature. And for the H, you will, for now, for the second trial, let's say this is the coefficient of heat transfer.